Alrighty, guys. Hey, it's Mr. Peterson. Sorry I couldn't be there today. I know you'll make me proud with the substitute teacher, whoever you have in there with you. Remember, you have two options today. Option number one is do nothing, and you're not going to get better. Option number two, use this opportunity to really dig in and get yourself better by following along with me and continuing to learn. So remember, the test is going to be on Tuesday. Keep that in mind, and we still have some stuff that we need to learn before then. So let's jump right in. I would suggest pausing and giving this warm up a shot before you listen to my explanation. So I would do that right now. Now, hopefully, you're done with the warm up at this point, and you've identified that this guy looks like it's multiplying by 2. Let me get my pen. Let me get the right pen here. Okay, it looks like it's multiplying by 2 from 6 to 12. All right, so we're multiplying by 2. From 12 to 24, again, multiplying by 2. 24 to 48, again, multiplying by 2. Now, remember, yesterday we talked about repeated multiplication. Now, when we have repeated multiplication is geometric. All right, that's going to be a geometric sequence. So this tells us right off the bat here that this must be a geometric sequence because we're not adding or subtracting to get to the next term. So for number one, what do you notice about the sequence? How is it different from the arithmetic sequences we discussed? Well, that's basically it. We have repeated multiplication, which makes it geometric. If it were arithmetic, then we would be adding and subtracting. Now, the initial value, also known as the IV, the IV is just equal to the first term, and the first term in this case is 6. It's just simply the first number there in the sequence. Now, I like to see this visibly as a table. So if you were to make a table here, you could see that 6 is the first term, 12 is the second term, 24 is the third term, 48 is the fourth term. All right. What is the ratio? That's just simply what you're multiplying by, right? So the ratio, in this case, what we are multiplying by, that repeated multiplication, is going to be 2. Now, the next three numbers, you would just continue to multiply by 2 to get to the 5th, 6th, and 7th term. So you could do that. Just continue this pattern on here for the 5th, 6th, and the 7th. And again, if you continue to multiply by 2 all the way through, you're going to get 96. And use a calculator to get to the 6th and 7th if you need to. But you would just continue with that common ratio of 2 to get to the 6th and 7th terms. Now, when we look at this next sequence here, 48, 24, 12, and 6, be careful here. Okay, now this is decreasing, right? Now, when we have an arithmetic sequence and it's decreasing, that is subtraction. But this is a geometric sequence that is decreasing. So from 48 to 24, what are you doing? Well, you're dividing by 2. From 24 to 12, once again, dividing by 2. And from 12 to 6, once again, dividing by 2. Now, you can think of that as division. That's fine. But later on, when it asks you for the ratio, like right here, you need to make sure that you do not say the ratio is equal to 2. That is not the case. That would be bad. Because if the ratio was 2, cross that out. Do not do that. If the ratio were 2, that would mean that you're multiplying by 2 to get from one term to the next. In which case, you'd have an increasing sequence. And this is clearly not increasing. This is decreasing. Do not say your ratio is 2. So dividing by 2 is the same thing as, and I'm actually going to erase this. Oops, let me erase it. Let me get the eraser out here. Dividing by 2 is the same thing as multiplying by 1/2. Multiplying by 1/2. Multiplying by 1/2. If you were dividing by 3, then your ratio would be 1/3. If you're dividing by 4, your ratio would be 1/4. If you're dividing by 10, your ratio would be 1/10. So you have to be really careful here. Your ratio is not 2. Your ratio is 1/2. Okay, so let me put that here. Ratio would equal 1/2 because you're cutting it in half each time, right? yeah, how is the above sequence different from the first sequence? The first sequence was increasing, whereas this sequence is decreasing. It's all about increasing and decreasing, right? This one was getting bigger as we went up. This one's getting smaller. So increasing versus decreasing. Now, what would the next three terms here be? Well, if we continue to cut these in half, we would get, let's see, this is the first, second, third, and fourth terms. Now we want the fifth, sixth, and seventh terms. Again, you're just going to continue to cut this in half. So what's half of 6? Well, it's 3. What's half of 3? Well, that's going to be 3 halves, right? Or you could do 1.5. And then what's half of 3 halves? Well, that's going to be 3 fourths. Okay. And again, if you're not sure where that came from, it freaks you out a little bit, just go to Desmos Scientific, the calculator, and multiply 3 by 1/2, and it will give you 3 halves. Multiply 3 halves by 1/2, and it will give you 3 fourths. Just use a calculator. Don't be afraid of fractions. Go to Desmos Scientific again, punch in 3 halves, multiply it by 1/2, and it'll give you 3 fourths. Trust it, and you'll be good. Okay, and that's the warm up. Okay, so be aware of what our learning goal is today. Just one learning goal. We are going to model these sequences we've been working with, and the 2 sequences we've been working with are arithmetic and geometric, and we are going to model them in tables, graphs, and as expressions. Feel free to go and do a little research on what dependent and independent quantities mean. Okay, do a little research there on that. That's important. And then let's take a look at example 1. So example 1 has us recall the following pattern from the day 2 notes. I think that you guys had noticed that basically we're just adding dots on each time. And from here to here, we added 4. Yikes, that is messy. Let me clean that up. From there to there, we added 4. And from here to here, once again, we add 4. So if we have repeated addition, let's just type that out real quick. Repeated addition is arithmetic. Okay, so in this case, we are, I spelled that wrong. Repeated addition, we are working with an arithmetic sequence here. All right, so now we need to make a connection here to a table. So at the beginning, there was 1 dot. At 1 minute, there was 5. And at 2 minutes, there are now 9. So when we throw this in a table, this should make sense, right? So at 0 minutes, no time has passed. We start with 1 dot. And at 1 minute, there's 5, 2 minutes, there's 9, 3 minutes, there's 13, and so on. So this is an example of a table. But if you want to get to the 100th term, right? I mean, you can sit here and do this 99 times. Remember, it's always 1 less than the term number. In this case, the term number is 100. So if we want to get to the 100th, we're going to have to add 4 99 times. What we established in the day 2 notes was this explicit arithmetic formula, where D is the common difference, and we're going to add that common difference, in this case 4. We're going to add that common difference of 4, n minus 1 times, on top of the initial value, or the first term. Now, when we throw that, oh shoot, sorry about that. This got erased a little bit for some reason. That's supposed to say term number. Sorry for the confusion. N is the term number, D is the common difference, A1 is the first term. So when we throw that in and we want to find the 100th term, you're just simply going to throw in 100 in for N. A sub 100 is equal to the common difference of 4 times 100 minus 1 plus the initial value of 5, right? Because we're going to add 4 on top of 5 99 times. So ultimately what that becomes is 401. So the value of the 100th term, if we were to continue to add 4 99 times, would be 401. Now, if we want to find T and we want to come up with an expression, the expression is just simply going to be the common difference of 4, and we are going to add that on top, T minus 1 times, plus the initial value of 5. So this right here is going to be our expression. That's it right there. Let me highlight it. That's your expression right there. You can use t, you can use n, you can use whatever you want. In the explicit formula, it uses n. Okay, but if they're defining the variable as t here, then you just simply use t in place of n. So 4 times t minus 1 plus 5 is going to be your expression. Now, when we're plotting these things, pretty simple, right? At 0 minutes, there was 1 dot. So at 0 minutes, we're going to put 1 dot. So that's going to be right about, oh shoot. So this is going up by, this would be 2 right here, right? So it's going up 2, 4, right here would be 6, and then 8, and then this mark would be 10. Don't have to put it. But the first mark right here at the 0th would be 1. Now, how many dots are there after 1 minute again? After 1 minute, there's 5. So at 1 minute, we're going to trace up to 5, which would be right about here. And at 2 minutes, there is 9. So we would trace up to 9 right about here. And then so on. At 3, there was 13. That's going to be right about here. Now, hopefully you're seeing a trend. What does this make? What does this make? And I wish I was there with you in the class to get fired up and excited about this with you. Arithmetic sequences, when you graph them, they're going to make lines. Okay, this is a linear relationship. It's going to increase with a constant common difference, which we're actually going to start calling slope here soon. Okay, so that's what it's going to end up looking like graphically. All right, now looking at example 2, recall the following pattern from the day 3 notes. That would have been just yesterday. So at the beginning, we're going to call that the 0 minutes. There were 3 dots, and at 1 minute there were 6 dots, and at 2 minutes there were 12, and at 3 there were 24, and so on. So we can see in the table here, this is not repeated addition. This is, oops, see? I mess up too. This is not repeated addition. This is repeated multiplication. And when we have repeated multiplication, it is not arithmetic. It is actually the other thing, that other thing being geometric. So this is a geometric sequence. Now, the geometric formula that we talked about right at the very end of class yesterday was this thing, where A1 is the initial value, or the first term, means the same thing either way, where R is the ratio. Okay, the ratio is what you're multiplying by. So what I threw in here is 6, that's the first term, and 2, that is the common ratio. So when it asks for at 0 minutes, how many dots are there? 3. At 1 minute, there's 6. At 5 minutes, there's 96. Well, at t minutes, t is just any desired minute. If we wanted to find the 100th minute, what would we do? We would plug 100 in for n. If we wanted to find the 67th, we would plug in 67 for n. But in this case, they're not using n, they're using t. So again, don't freak out. They're just variables, the same thing. So we're going to say, okay, well, our initial value is 6, and we are multiplying 2 t minus 1 times to get to whatever desired term number it is that you want. So this right here, boom, is going to be the expression. Okay, it's just this. It's the same thing. It's just using t instead of n. Same difference. Now, when you plot this thing, let's see what happens. And we're gonna do it roughly here, right? Because this is going by tens. So 3 would be about there, roughly, right? So the 0th term would be right about there at 3. 1 would be right about here at 6, just roughly about half of 10, right? Just slightly above. 2 would be at 12, just slightly above 10. So about that. This is just kind of approximated. 3 minutes would be 24. So again, just kind of right here between 20 and 30. 4 would be at 48. That's going to be real close to 50. Hopefully you're seeing here that this is not straight. This is not linear. This is different, right? Arithmetics are linear. This right here is kind of curvy. I hear a lot of students say that. It's curvy. It's not straight. It's curvy. Now, when it's curvy like this is not linear. This is what's called an exponential function. And we're going to talk a lot about that in the next season, our next unit, functions. So for right now, you could call this an exponential function if you want to get fancy on your test. But this is also just known as a geometric sequence. And geometric sequences do not make lines. They make curves. It's kind of curvy, right? So that's an increasing exponential function for a geometric sequence. All right. So now let's look at our boy Scott here. Scott has decided to add push-ups to his daily exercise routine. Good for him. He is keeping track of the number of push-ups he completes each day in the given bar graph, with day 1 showing he completed 3 push-ups. Well, our boy Scott here looks like he's getting stronger at an arithmetic pace, because it looks like he added 2 on after day 2, 2 more on after day 3, and 2 more after that for day 4. So you can see this is the arithmetic change here. We are adding 2 each day. So he's getting stronger. Boy, Scott, keep doing them, man. So he's getting stronger. He's doing 2 more each day. So instead of drawing this thing out, when we ask how many push-ups can Scott do on day 10, I don't want you to draw out 10 more pictures. I don't want you to keep on adding 2. I want you to use the formula. So pause here, give it a shot, and when you unpause, the answer is going to magically appear. So pause now. All right, hopefully you're looking at something like this. So here is our arithmetic formula. Here is our arithmetic formula with the common difference of 2 and the initial value of 3 added in. And here is the work for finding the 10th term. Okay, so the value of the 10th term, if he does this for 10 days, Scott is going to be doing 21 push-ups by day 10. Now, what we just did here, this is solving for it algebraically. Okay, and you're going to have to be able to do that on the test. Now, let's throw this in the table. Again, I would pause now that you've had a couple examples up above where you worked through with me. Give this a shot on your own and see if you can throw this thing into a table. Pause now. Okay, hopefully your table looks like this. After 1 day, he's able to do 3, 2 days 5, 3 days 7, 4 days 9. It's okay if you did 5 days here. I just threw 10 in because we knew at the 10th day's number of push-ups were 21. Hopefully you got this though. This is what our expression is looking like. So if you want the nth term, it's just going to be 2 times n minus 1 times. Remember, it's always 1 less than the term number you want. And you add on the initial value on top of it. So that's going to be your expression to find the nth day. Not the second day, not the third day, not the fourth day, not the 68th day, but the nth day, right? It's going to give you any day that you want when you just plug in for n. Now, again, pause here and give it a shot plotting these things. As we know, this is arithmetic, and arithmetics should make a line, but give it a shot. Go ahead and pause. All right, and it should look something like this. I plotted 1 and had 3 right here. I plotted 2 and had 5 right here. I plotted 3 and had 7 right here. And eventually I just got tired of counting up and over and out and over. And I realized that, hey, we have a slope here. Up 2, run 1. Up 2, run 1. Up 2, run 1, and so on. Remember the rise over run slope stuff? Up 2, run 1. Up 2, run 1. And I just kept on following this pattern. And I checked it, and I saw that on the 10th day, did we have 21? Let's see, the 10th day would be right here. And on the 10th day, boom, yes, we had 21. So we had done that correctly. All right. So now we need to write an explicit equation. And remember, the explicit equation is just simply a sub n is equal to the difference n minus 1 times added on top of the initial value. And when we throw this in, again, it's just your expression, right? This is an expression. Remember, we talked about this yesterday. An expression doesn't have an equal sign, but now you need to have an equal sign if you're going to make an equation. So you're just simply going to go a sub n is equal to the difference 2 times n minus 1 times plus the initial value of 3. Boom. That's going to be your explicit equation with your common difference and your initial value tossed in. Finally, do not worry about this pair deck. You guys are all set to go. Feel free to go through these extra resources if you feel like you need some additional help. At this point, guys, this is it. So there is no new content before the test on Tuesday. We are going to review on Monday. So at this point, you're just going back, making sure you've done all your self-assessments, all your portfolios. If you've done all that and you feel like you still need some extra help, this is where you're going to start hitting up these links and doing some extra practice. And then on Monday, we'll wrap everything up together. I'll get questions answered for you guys, and then we will test on Tuesday. All right, you guys, have a great weekend.